Okay, we're good. We're rolling.
All right. Okay, so the question was about the third programming project, where we've got, that is a persistent homology computation. So the point is that you want to build a bar code. A bar code is a list. It's a Python list of bars. Capital B bars. Each bar, well, it's an object with a bunch of methods and a dot vectors field, a vectors attribute. And the way the vectors work is it tracks the history of a particular basis vector in your barcode. So remember what's going on. If I have a V0 into V1 into V2, etc., this is my quiver representation. I build a basis. So V0 is equal to span of B0 up to Bn. And this one also has a span, but I'm interested in knowing where each of these basis vectors go when they go through V1, or when they go into V1. And so what the bar object is supposed to do is it's supposed to track the single history. If I call this one M0, M1, this is going to map into M0, B0, and that's going to map to M1, M0, B0, etc. So a single bar object is tracking this history. This is one bar object. Now, if the bar starts at the beginning, the vectors field will be a list, B0, M0, B0, M1, M0, B0, etc. So the matrix product of each of these guys as they go along. Now, if that basis element doesn't actually show up here, it started here, say that this particular vector space is a bit larger than the image of M0, then there'll be some bars that were born here. And if one of those vectors was born here, what you do is you need to put a placeholder into the vectors field to say that we're starting off here. The vector in question is not present here. So if the bar is born at some later time, you pad the vectors field with nones. So, for instance, if you're born at time 2, let's say you had a bar that started here, Cn, and it's going to keep going, 2, etc. So there's nothing leading up to this one. Then you'd see something like none, because it's not here. It's not here either. None. And then it shows up. Now, if the bar dies, you have two options. Option number 1 is just stop adding to the vectors field. The other option is just append nones. I think my tester is compatible with both. Should be anyway. If it's not, let me know. I'll fix it. So for instance, if you have a bar that is born at time 0 and dies at time 1, the first case it would look like B0, B1, and it just stops. The second one would be B0, B1, none, none, etc. I'm just following here on out. In either case, a barcode is a list of these bar objects. What I'm keeping track of here is the vectors field. You could have, well, just imagine that I didn't have bar objects, I just had list of lists. The thing that I found is list of lists tends to result in forgetting exactly what all those lists meant. Having a separate type kind of makes it clear what's going on. And furthermore, having a bunch of methods that you can ask for, is a particular bar alive, as in, is the most recent entry none or not, is useful. So it'll check the last entry. So if there's an is alive method for the bar class, what it'll do is it'll look at the very end. It's compatible with, it's assuming this kind of structure, not this kind of structure. It checks to see if the last entry is none.
Right.
If you're using this convention, do not use the is alive method.
Okay. It's just a good argument to use
Yeah.
the second.
It's a good argument to use the second approach. Yeah. Yeah.
So is the first part is, this is all problem 2?
It's all problem 2. Yep. This is problem 2. So problem 1 doesn't involve this. However, it is motivation for why in problem 1 I ask you to return nuns in certain spots. It's a very reasonable thing. In fact, the way that I first wrote that, so the way that I make the projects is to write the code myself and then pull the problems out of it. So I wrote the first problem, or the answer to the first problem, said, well, any vector that ends up being linearly dependent with the rest, just throw it out. And then I realized that if I have a bunch of vectors, now I've lost track of the order.
So if we wanted to create nuns, why not? Wouldn't it be easier to just make a nunnery?
I can hear the setup for that from a mile away.
Indeed. Indeed. Anyway, all right, other questions on this? There we go.
So if we're going to use the method you give us to expand the basis, we want to already have most of our bars to hand it what we're
That's right. You're going to hand it the most recent vectors available here, and it will give you back a bunch more.
So it's, I was thinking of starting with one, running through it, and then starting with then doing the next, and then checking against it. That wouldn't work to expand the basis.
No, that wouldn't work to expand the basis. I mean, you could do it that way. You could do it that way, that I start out here, build out all this entire bar, and then go to the next one and try to build out that whole bar, and then you fill that out. Then go to the next slot, expand the basis, and then follow each of them in turn and recursively examine this. You can certainly do that. It's not, I built it iteratively like this, one stage at a time. So I have a bunch of bars running, and then I extend the bars as I go, rather than filling out an entire bar at a time. But you certainly could do it, you could certainly build it out bar at a time. Other questions? All right, well then, let's pick up where we were last time. Last time we were going in the direction of manifold learning and learning the homology of a manifold. We defined the concept of manifold. Now we need to dig into that definition a bit and pull out a bunch of useful things. No. Okay, so we're looking at manifolds, manifold learning, and homology learning. So last time we had defined what a manifold was. which is, what is a manifold? It is a topological space. Yep, topological space with a maximal atlas. Right. And the key thing about atlases is they tell you locally what a Euclidean coordinate system looks like. So each chart of an atlas tells you a local Euclidean coordinate system. That's the point. Okay. Now, there are lots of cool things you can do with this. And in order to make use of manifolds in the practical sense, we need to put them somewhere. We need to put them somewhere where they can interact with data. So here's the point. These are abstract in the sense that they're defined intrinsically as a topological space with an atlas. What we want to do here is we want to connect to the data. And usually, what one wants to do, this is in some sense a souped up regression, is your data are a number of points in Rn. Set of points in Rn. So we want to connect a set of points in Rn and use that to estimate a manifold. Now, this is kind of the same place that persistent homology was working, which is set of points, we build a Vietoris-Rips complex, and we study that filtration, we compute persistent homology to try to understand the homology of the space. Now, and what we also want to, well, what we want to do here is a little different. We want to build a manifold out of that. That's manifold learning. As in come up with an atlas to describe locally what the set of points looks like. Or, if we're interested in the homology of the space, it's essentially the same kind of thing as what we did before with persistent homology. We'll see there's a nice interaction. Okay. So, let's sort of delve into the setting. Setting. We have an unknown manifold M and an unknown smooth map. To Rn. So we have an unknown M, unknown smooth map. What we do know subset, usually, but not always, a finite subset, P of Rn, presumed to be near the image of F. Task, find M and F. So pictorially, something like, got a bunch of points that are kind of near the manifold, or kind of near the image of the manifold through this smooth map. I'd like to come up with some kind of description of the manifold and the smooth map. Of course, as stated, this is a completely ill-posed problem. You'll have absolutely no hope, and I can throw plenty of counterexamples to break anything you think of. Bad news. So there are some constraints that you need to apply to make this reasonable. Okay, so picture. Here's R2. This is your input. You want the output to be this. Say the domain is a circle, and F traces out this particular picture. That's the goal. That's what the manifold learning is about. So how are we going to do that? Well, the way we're going to do that is we're going to study a particular kind of smooth map, and assume that that's what we got. We're going to assume that we have that smooth map that makes something whose image is itself a manifold. It's a submanifold space. So M here, it's a manifold in its own right. It's a one-dimensional thing. Its charts are built around mapping bits of this thing down to line segments. Over here, my charts map parts of the plane, R2. So this is in R2. This maps bits of the plane to R2. So there's a dimension difference right off. So the tool, we need some assumptions to constrain this problem. The tool is the notion of submanifolds. And submanifold charts. So, what a submanifold chart is a chart in which, well, it looks like this guy's been straightened out. So, if N is a subset of some manifold, this is a manifold, this is a topological space, a submanifold chart for N at X in N is a chart. I'm going to take an open subset of M to Rn, in which the image of N, well, I can't write the image of N exactly like that. I have to only look at the part of N that appears in this open set, in which this image lies on a coordinate plane. Here's a picture. Here's a U. Here's a phi. I'm going to map this into R2. Here's the origin. And this guy here is the image of F. So it lies on the x-axis, for instance. Now, of course, I can't flatten the entire circle down to a single line, but I can do it bit by bit locally as I scan around here and come up with lots of submanifold charts. Now, the cool thing about submanifold charts is if I restrict my attention to that coordinate plane on which it lies, in every one of the submanifold charts, I end up with an atlas for that sub-topological space. So, very, very easy proposition.
saying that line is the end of?
Yep, the line here, this heavy line, is basically this curvy bit has been straightened out. Now, how do you do that? Well, I don't know. At this point, I'm just saying, I'm defining, if you can do that, that thing is a submanifold chart. Now, if I have a collection of submanifold charts for a topological subspace N, then they form an atlas, it's not maximal, they form an atlas for N. You can extend that to a maximal atlas, built out of submanifold charts, and that's a submanifold. So, definition. If N is a topological subspace, in which topological subspace of a manifold, and in which every point of N has a submanifold chart. Then N is, number one, called a submanifold of M. And that's a definition. Here's a proposition. It is a manifold. Its own right. It's a manifold of its own. Now, the proof of this proposition is basically pretty easy. All you do is you take each of these submanifold charts, you restrict your attention to just these sets as the domain. Pre-images of open sets are open, so basically that you just pull that back right from every submanifold chart here ends up being a chart over here, and you're good to go. That's really
Is that only true if the function is continuous?
in fact, it's only true if the function is smooth. If it's continuous, then I have a topological manifold. If it's smooth, then it is a CK manifold. Yeah. But yes, strictly speaking, I absolutely need continuity. So yes, the basic idea is use continuity of F to transfer each submanifold chart to a chart on an open set. That's the basic idea. Basically, the idea is I have this open set U. If I look at the pre-image, this is F inverse of U. And then the map, F and then phi, so phi compose F if you write it out, this map followed by a projection, throw away all of the junk here. So first do F, then do phi, and then squash. This thing is then a chart over here. So throw away all the coordinates you don't need. PR for projection. So basically, it lies in a coordinate plane, so just map, I never actually get to points out here, so I'm going to map them down to this, basically vertically here. I never actually ever go there, so it doesn't even matter one bit what I did. But now this is legitimately a function from, say, my space to R1 when I do that projection. So actually, strictly speaking, that goes here, and then I go one more, I guess you're right, PR this thing here, this is my chart. Anyhow, that's basically the idea. Yeah.
So, as long as the shape at the end,
As long as I've successfully flattened it everywhere, yeah.
hmm,
Because everything needs to, the image of this map needs to, or the image of this space here in the map has to lie entirely within one of the coordinate planes. So I flattened.
so then wouldn't smoothness then be sufficient?
Smoothness is certainly sufficient, then I get a smooth atlas over here. If I could only do it up to continuity, then I end up with just a C0 atlas. So, in fact, the continuity of the M, the submanifold, is bounded above by the continuity of the atlas that started with over. So if I have if this is a smooth manifold, then I could potentially get smooth submanifolds. If this is only a C0 manifold, then my submanifolds can never be anything more than C0. Yes?
Smooth as C1, right?
Yes. Smooth is C infinity. Yeah. Yes?
What does the manifold consist of? I thought a manifold was a
Topological space
set of atlases that
with
are,
a collection maximal atlas, with a maximal atlas.
so it's the collection of the
Right,
charts.
it's a topological space and a maximal atlas, so a collection of all the charts.
Okay.
All the charts that are compatible with one another, as in when I try to take a look at the intersection, I've got a nice coordinate transformation between them.
But it's the space itself also.
It is a space in its own right. Yes. Okay.
Well, what kind of?
Topological space.
Top what?
Topological space in the top. Okay. Now, submanifolds are what we want to work with. And really what we do manifold learning, we're doing submanifold learning. Here's the idea. If I have a smooth function, like plain old calculus smooth function, and I look at its graph is a submanifold of Rn plus 1. Why? Well, what's one of the first things we tell you about with calculus? What do derivatives do? They find what?
Limits of difference quotients.
Limits of difference quotients, and then what's the geometric interpretation of that?
Rate of change of a line.
Rate of change of lines, slopes, tangent lines. What we're doing is we're finding tangent planes. What we're doing, this origin point is some point here. By flattening this out, all of these guys here are basically tangent lines over here. So let me show you how that works. And then that's the key insight that drives the concept of manifold learning. And it also is the key geometric insight we need in order to determine homology of manifolds and point clouds. But the key restriction that makes this problem go from ill-posed and unsolvable is the fact that we're looking for specific submanifolds. Not just any old function, we're looking for submanifolds. Okay, so, example. If f going from R is a smooth function, let's say. Then its graph, set of all points x, y, such that y is equal to f of x, is a smooth submanifold of R2. And in fact, better than that, put an Rn here, and then it's Rn. Let's go. Okay, so how does that work? Well, goal, find submanifold charts. How do we find submanifold charts? The insight is that these are found by derivatives. Not exactly derivatives, there's a little bit more to it, but we'll see that. So let me get a picture up on the board. So let's see what's going on. Here's x, here's y. Just come up with a little calculus function. Here's a point x, here's a point y is equal to f of x. So roughly speaking, what we want to do is we want to smooth out, and we want the image, the graph, this blue thing is, this blue set is G. This is the tangent line, this is the line y is equal to x times f prime at, let me call this x0, at x0. In fact, let me write down Taylor series-wise, right? F of x0 plus f prime at x0 times x minus x0. There we go.
Where did G come into this?
G is the graph. It's this blue set, subset of the plane. It's the set of all x and y, such that y is equal to f of x. It's a graph. That blue set. So what we want to do is we want to come up with a submanifold chart for G centered at x0.
So now I just thought G was the area inside the box.
Oh, no.
Yeah, right.
No.
Yes,
It's just this
yeah.
curve here. Right. So we want to find a submanifold chart at x0. Well, the thing to do, really, is we want to force what? Well, we want to force the curvy bit, the G, to lie entirely on the x-axis in our chart. We have lots of charts that we could pick. We want to pick a particular chart so that the curvy bit lies in the x-axis.
What is the curvy bit?
Curvy bit is G. Sorry, I'm not being very precise with my
Curvy
name.
bit to lie on the x-axis.
We want the curvy bit to lie on the x-axis.
Cool.
Alright, so how are we going to do that?
Hit it. Down. Can't do that.
You get out a hammer and start tapping.
Let's take, I don't know, can we squeeze it with other functions?
Well, we can rotate it, first off. The key thing is that we can rotate it so that it's mostly linear, and then the rest perturbation is not so much.
So we just project it?
And just project it. Yeah. How do I know that projection is not going to cause any problems?
Vertical line test?
The line test is a function. Now, how do I know it's smoothly compatible? I need coordinate transformations from one to the next. Right. So, general idea. Is project vertically. So let's say I have x minus x0 minus epsilon, x plus epsilon. That's-
X0 plus epsilon?
X0 plus epsilon, absolutely. So I want to build my chart, which is going to be on this set here. I want a submanifold chart. Well, I'm going to make a submanifold chart on this kind of set, this strip. So I'm going to build my submanifold chart to be my open set like this. And my phi is going to be project onto the first coordinate, i.e., which is phi of x, y, which is x. Now, how do I know that I take a collection of these submanifold charts that they're going to end up, first of all, doing the right thing when I have a neighboring chart? First of all, observe. Okay, so here's the problem. That's the first, this is, strictly speaking, this is not a submanifold chart. It's close though.
Phi is not a submanifold chart?
Yes, so the pair, this, U comma phi, is not a submanifold chart for G. Why not?
It's gotta be a homeomorphism,
Yes?
bijective,
Yep.
homeomorphism.
So bijective homomorphism, sure.
Take the inverse.
Yeah. And?
Is it bijective?
No.
So. then it's
Oh,
not-
yeah.
Right. So projection is a good idea, but it's not it.
Hmm.
It's not it, because it's not homomorphism. And it's not even bijective. Right. Not just bijective. Okay, so projection, though, it kind of seems like the right thing to do, but it doesn't quite work.
Could you explain mathematically what a projection is? Did we talk about this?
Sure, projection is take every point in here and map it down to there.
Right.
So projection, all it does is it takes a ordered tuple and gives you back some of the tuple elements.
Huh.
That's it. Now, more abstractly, a projection is a kind of map that is idempotent. You do it once, it's the same as doing it twice. I squashed it down, and now when I run it again, it doesn't do anything else.
Right. So it's already squashed out.
It's already squashed out.
Huh.
It's a particular kind of idempotent map. Okay. So this doesn't quite work, so we've got a bijection problem. So how do we fix that? Yeah.
If the image, if the function is f, right? And we took like kind of f inverse to map it basically back down to that point on the real line, or to that subset of the real line. Couldn't we just map it back up to the red function, to y function?
Yeah, kind of.
So
But remember, we're still fighting the same problem. We still need bijective. It's
And-
not helping the bijective problem. Remember, the moment you squash down to here, we're going to lose bijectivity.
You can't have an inverse function
Right.
without bijectivity.
Right, so what we need to do is we need to do something a little different. What we need to do is we need to get all of the points in the vicinity in the plane. We need all those points in the vicinity of the graph. Maps to something that's going to look a bit like, I mean, this is the goal. It's going to look like that. That's what we want. That would be a bijection. Right? That's a bijection. And furthermore, the image of this G thing is in fact the x-axis in this plot.
So it's always when you just,
So yeah, projection could be part of it, for sure. But you got another coordinate to worry about. Yeah.
What was the problem with the first bijection?
Well, the first thing is a bijection.
No, well, because it wasn't one-to-one, or because it
Yeah, it's
wasn't?
not, no, it's not, yeah, it's not one-to-one.
Think about all the things.
Right, everything vertically here is gonna get mapped to the same point.
I thought we were only taking points on the graph.
No, we're looking for a submanifold chart, which means it's a chart in the original manifold, which is R2.
Well,
R2,
that's super
Yeah,
complicated.
yeah, right.
R2, I gotta take all the x, y coordinates. If
Yeah,
we just do a
okay.
projection, now I'm in trouble.
Yeah, yeah.
So what am I gonna do? How am I gonna make this happen? Well, I can certainly use the projection as the first coordinate. That's totally legit, but now I gotta do something to the second coordinate. What do I do to the second coordinate?
Hang on a second, so you want to take R2, which is two-dimensional.
Yep.
You want a bijection between that and this line?
No, this
Not
is
possible.
set, this set. Take this region, map this region to this region. This is a subset of R2, this is a subset of R2. Now, I think what you're struggling with is the fact is that I may stretch this thing out a lot.
No, the picture was just a little confusing.
Okay.
So what's the target in that picture?
The target is this point. So this point here, x0 comma f of x0 maps to the origin.
Okay. I believe that this is possible.
It is not always possible. It relies very heavily on the fact that I've got a smooth function. I can't do this if I don't have a smooth function. If I were to put double staircase here,
Yeah.
I'd be in trouble.
So basically anything on that red line needs to be mapped to 0. Or
Well,
it needs to be, or sorry,
no.
anything on the blue line needs to be mapped to the
everything
x.
in the blue line.
Needs to be mapped to the x-axis.
Right, so that's where the projection is a good start. So what does the second coordinate have to be?
Oh, I see.
What does the second coordinate have to be?
Did you arrange that whole circle or just the line?
The range, everything in here goes everything in here.
Okay.
Yeah,
Could it be the Cartesian distance from the arc?
certainly could. Could also be a little more simple than that. That's kind of overkill.
Okay. The vertical distance from the arc?
Yeah.
Okay, yeah. So how?
Y minus,
Yeah,
Yeah, we just stretch it.
f of x.
now we're in business. Now we're in business. So the projection is the first one. Second one, not projection, but now we're in business. Now why are we in business here? Why do we not run into problems with bijectivity here?
Because the only things that are sloped, everything's set.
Yeah, the problem is when you set vertical line test, it's because f is a function. That's helpful. Now, I may still run into problems with smooth compatibility between these various charts. If I put the Weierstrass function here in for f, so the double staircase, well, this is still a bijection.
But haven't we defined f to be a smooth function?
No, yeah, I understand that. But what I want to know is why is that necessary?
Okay.
Why is this necessary? Thus far, it hasn't been necessary. This is bijection, so long as f is a function.
Yeah.
So this is always a bijection. The problem is that if I were to choose another neighboring such set, slide it over a little bit. In particular, now, slide it over a little bit, I've run into problems. Because my transform from one to the next would no longer line up. So, what about coordinates? Think of it this way. What I really want to do is I really want to center this guy. Let me make a modification to make this a little clearer. What I really want is this thing here puts you down onto the x-axis wherever you are. I'd really like to be centered on 0. And if I really would like this to be centered on 0, this should be centered. It should be something like this. Phi of x0 is x, y is and now this should be f of x minus f of
Should it still be y minus f of x?
this should be y minus f of x. Yeah. Now my curve is squashed down to the bottom, but I've centered myself on the origin.
Now, did you say the domain was this circle here, or was the whole of R2?
So, here the domain is all of R2, sure, it works perfectly fine. I don't need this. Right, so your question now is what's the domain? In this particular case, for this function, it's everything. Now, this also could be a smooth chart. Is this chart smoothly compatible with this one? Only if f is smooth. So this new chart is smoothly compatible with this one. First, when f is smooth. So that's where we're using the smoothness. Which is to say, I'm going to take it, I'm going to invert it, and I'm going to process through. How do I know that this function is invertible over an open set? It's because it's locally linear like this. Okay. This picture is now actually the way you do a manifold learning. And the way this works is the following. I'll take a little bit of a geometric detour. And then I'm going to zero in on what we want. So, geometric detour. So, if we have set X is a subset of M. Actually, let me call it not M, let me call it Y. There. Y is a metric space. The reach of X and Y is the largest, the maximum distance is that every X, right, not every Y in Y delete X with the distance between Y and X is less than the reach. Such that every Y outside of X, but within the distance given by this reach, there is a unique X star in X closest to Y. It's a lot of words. Let me give you a picture. I'll give you several pictures.
Is this statement
Should-
that,
I'm defining reach.
Is there there's a unique X star in every X closest to each Y in Y, or just, yeah,
So the quantification is I'm going to pick a Y,
right, and then there's,
and then there's a closest one.
okay,
So,
I was going to ask if X subset of Y, where Y is a metric space, is a type error. Because metric spaces aren't technically sets, they're tuples.
of course, it's a type error. Computer scientists, beware. Yeah, I mean subset of the set part of the metric space. All right, fine. Okay, thank you, Abby. All right, actually, this is kind of too complicated. Let me make a some slightly easier example, right? Make a pinch. Okay, so I've got a little pinch point. This is X, and Y is equal to R2. Okay. The reach of this set is basically well, half this distance. Because if I pick some point that's within half that distance, I'm uniquely closest to one point, but if I pick something that's right at that distance or whatnot, then I can end up getting close to multiple points here. Another example, this set, this is x1, x2, the reach of x2 is 0. There are lots of points, no matter where I move my y around. Regardless of the distance you pick, it's going to be close to multiple. So if I put a y along this dotted line, I can move that y as close as I like to x, and I'm always going to get 2 points nearby, one on the top and one on the bottom. So if I pick a y here, closest point is up here and down here. If I pick a y a little closer, say maybe I'll fix that problem. Well, nope, always got 2 possible closest points, and I can just keep sliding that y in all the way. So do I have a quantification problem? This is over, I have a single reach over all y. This top one here, there is a particular reach, because everyone that I pick within, what is
Right.
it?
Is this conservation such that every y, so every y in R2, except deleting that line x1,
Which
should
has-
be less than the reach?
Within this region, yes.
Yeah, so I think what Chris is saying is that it should be that there exists
It should
such
be-
that for all, instead of for all there exists.
Let's see here. Oh, I got backwards here. So is such that,
Yeah, pretty much.
is the maximum distance such that for all, wait.
Because if you say for all first, there exists, there can be many of them, but if you say exists.
Well, there are
such-
many possible reaches.
The thing is, because if that's the case, then shouldn't the reach technically for both of those still be infinity? Because if I pick a y that's arbitrarily far away from that graph x,
Yes.
the distance between y and x is not less than 0. Like, that,
Wait. So let's see, it is the maximum distance. Okay, so it is a single distance. It is the largest such that every y within that distance has a unique closest point in x. So pick a distance. Let's pick a distance, say, call it this distance. Is it the case that every y within that band of points
So-
from here,
so you draw an epsilon neighborhood around x2.
right,
And-
and there's,
Within that epsilon bound, there must be a single unique x star for every y in there.
yes, and that's not true.
Okay, all
And
right.
that is not true.
That, all right, got it.
That
Okay.
is not true here.
Got it, thanks.
So I need to shrink my epsilon a bit.
Sure, thanks.
And the point is that I have to keep shrinking that and shrinking that more and more and more until I eventually just give up and say, nope, doesn't work at all.
Okay, thank you.
Yep. I think
Yep.
I see furrow grow still.
So symmetry is important.
So yeah, reach does detect symmetry. Reach, on the other hand, detects convexity too. So if I have a convex set, solid convex set, the reach of this guy is infinity. I could just keep extending this guy, and there's always a unique closest point.
So the reach is a function of y here?
It's a function of the space x living inside y.
Right.
Yeah. Yes.
The sets are defined using less than.
Mm-hmm.
If there's a unique solution,
Mm-hmm.
shouldn't it occur at a corner?
What?
If there's a unique solution, or not a corner per se, at an edge,
Yeah, it's going to end up on the boundary of the space, should that have a reasonable definition.
but the boundary of the space is not included in the
That's right, it's not included in this definition, that's correct. In fact, sets of positive reach tend to have very nice properties like boundaries. But in fact, this is a different way to get at some geometric properties of space. Now, I'll pull this all together. Pull this all together. So convex sets have infinite reach. Decidedly non-convex sets might not have positive reach. This guy here is an embedded submanifold. It's a submanifold of R2. It has a positive reach. So now here's the key theorem. This goes under the name of a tubular neighborhood theorem. Tubular. Totally true. And this is the key thing that drives the whole manifold machine. Theorem. Compact, smooth, submanifold of a space metric. So of a manifold metric, not just a space. And I'll put in here appropriate metric, as in one that yields the same topology on the manifold. Compact, smooth submanifold of manifold with an appropriate metric on that space always has positive reach. And by appropriate metric, I mean the metric yields manifolds. That's one that yields the right topology of the manifold. So if that's the case, then my sort of bigger manifold that's holding my submanifold is both a manifold and is a metric space. In that situation, then my submanifolds always have positive reach.
And by positive reach, you essentially mean
Not
not zero,
not
not
zero.
zero, and not infinity.
Not zero, it could be infinity.
Okay, so
Infinity
anything
is-
in the natural number.
Infinity is a positive number.
Okay.
Could be not even a natural number, could be some
Okay.
fraction. It's
Okay.
fine. Yeah, you can have reach of pi, it's fine.
Okay.
I think that if tubular neighborhoods existed, they'd be in California.
They probably would. Yeah. They probably would. So why is this called a tubular neighborhood theorem?
It's because it's used for helping people with floating pools.
Because you build the nets
So
on
we
a
can get
two-rounded
around
function,
The
right?
inner tubular.
Exactly.
neighborhood.
Here's my manifold N.
Sorry.
Just get the right answer.
I like the California answer better.
I think the California answer is totally fine. There we go. There's my tubular neighborhood around my manifold N. There's my inner tube around my manifold.
So is N the dotted line?
N is the dotted line.
So you
my
form
tubular
a
neighborhood.
torus around it.
Yeah, it's filled in a
This
solid
would be,
torus.
this would be for some curve n in R3,
That's right.
correct? Okay.
Yep. Now in R2, the tubular neighborhood is just an annulus.
Okay. Not R.
And of course, if you've got some other crazy manifold, well, submanifold, well, it's fine. I mean, in R4, you could have a Klein bottle and have a tubular neighborhood around that. Totally fine. This is what it is.
Cream-filled donut.
Cream-filled donut. Yep, cream-filled donut. Okay. Now, how does this, coming back to the manifold problem, how does this work? The point is, if all of those little points, now let's come back to our original context, where I have a cloud of points in Rn. So now, returning back to the main point. A cloud of points in Rn. So, facts. First of all, that tubular neighborhood has the same topology, like the homology. As manifold. It's not homeomorphic too, though. But it's homotopy equivalent. It has the same homology. So that's fact number one. Now, fact number two. Having sufficiently dense set of points in the tubular neighborhood, then via torus-Rips complex will recover with what radius? Remember, before we had to worry about choice of radius that led us to persistence. This is a different idea. With the radius equal to the reach.
It's just like coding theory,
Is it?
where you have, the idea is that, like balls around code words, and if you're under, is it D-1 over 2 floor? then you
Yes,
always
okay,
have-
yes, that's exactly this kind of theory.
Yeah,
fact-
that's what I was thinking of with natural numbers.
Oh, I see.
Yeah,
Got
it's
it,
a coding
okay.
theory, it has to be a natural number.
Got it, okay. Very cool. Yeah, fun fields and all that good stuff. Yeah, all right, awesome. Okay, so if you have this sufficiently dense set of points in the tubular neighborhood, then the Viator's-Rips complex is going to recover that topology, like exactly, once your radius is reached. Now, what's the sufficiently dense condition? You want enough points within my manifold here so that I fill out a certain dimensional simplex. I want to fill out that top dimensional simplex. So I need to have that many points kicking around there so that I actually fill out something that's got the right volume. So I need to have, if this is R3, I need to have 4 points within every ball of radius reach so that I get a 3-dimensional chunk all the way through this. Now, I might get some bigger simplices floating around in there, but they'll squash down.
Huh.
All right. Now,
So finding the reach is a real challenge.
finding the reach is the real challenge. And in fact, this is a pretty awful bound in practice, typically. Yeah.
But if we have some, suppose I'm doing an experiment,
Yep.
it's kind of expensive to do.
Yep.
If I keep doing it until I have met this condition,
Yep.
then I can stop.
Yep. Precisely. This is a stopping condition for sampling. Absolutely. Yep. So that density, that sufficiently dense set of points is need at least enough points in each ball of radius reach to fill out a max filling simplex. This is a very, very loose bound. There's some better bounds out there, but that'll certainly do it. At least in my own practical work, when I've collected data to do this kind of thing, it seems like you very often can get by with even as few as 20% as what this bound would suggest. You start getting reasonable results at that point. This is a very loose upper bound on the number of points you need. So if it says that I need 1,000 points, I can probably get by with 200.
So why isn't it, it seems like it should be a lower bound.
Lower bound on the number of, yes, it's a lower bound on the number of points I absolutely need to avoid problems.
Mm-hmm.
But very often I can get by with quite a bit fewer and still come up with reasonable results, even though they're not theoretically guaranteed.
Okay.
So it's the sort of thing that says, maybe I can't rule out all possible problems, but I'm still pretty decent.
So you have like an argument similar to convergence and distribution.
Exactly. Exactly. Now, The other point, which is useful here, is to realize that these submanifold charts themselves are quite useful. So if I have a bunch of points in a region, one thing that is pretty easy to do, and this is where I'll end the discussion today, one thing that's pretty useful to do, if I have a bunch of points, it's one of the easiest things that you can do as far as regression, linear regression. Awesome. So this can soup up. This needs to advance here. Not linear regression, but rather locally linear regression. Here's my point cloud. I'll spec this out. What you do is you pick a point. It's one of those data points. And you grab only the points in this region. I do a linear regression here. That is going to give me essentially a submanifold chart in the vicinity of that blue point in that green region. So only use these points in the green set. And with those green points, go ahead and get yourself a linear regression. Now, then what you do is then you pick another point that's not quite outside of this region, but sort of on the edge somewhere. Again, there's some sampling bounds. Pick another point. I'll put a circle. And grab a different region, the similar radius ball. Only use the points now in this region. Come up with a new linear regression. You come up with that new linear regression, that's like a submanifold chart for this circle point now. But over here, this other region. So now what am I going to do? Well, the realization is that I have a transition map for all of these points here. I can project them down to this plane or this plane, to those two possible linear regressions. And now I have a smooth transition map from one to the other. As I walk around the entire set of points, building out these local linear regressions, I've built out a collection of submanifold charts for this set of points. In essence, I've figured out a manifold structure for this set of points.
You're building like a polygonal approximation of this circle
That's right.
that gets better as the number of
Points gets better.
points you
And this
samples.
is, and this actually is this is the correct way to generalize linear regression to nonlinear regression. Because now what I've done is I've got submanifold charts for everything. This shape can be whatever it is, so long as the spread of my points is within the reach of the original manifold. I now have a family of submanifold charts for that, which means now I could just throw back and say, you know what? Abstractly, the space that I was sitting on was the manifold defined by this collection of submanifold charts. I've now learned the manifold structure. As that I've come up with a chart for the topological space defined by all of these points.
So each
I've come up with an atlas, rather, for the topological space with topology on these points. Therefore, it is a manifold. I have that full manifold structure.
each one of these regression lines is a chart.
Each one of these regression lines is specifying a submanifold chart. That's right.
And taken together, they specify the atlas.
An atlas, exactly. Taken together, they specify an atlas of submanifold charts, whence, by the previous proposition that we sort of sketched, is actually an actual atlas for the set of points with their intrinsic topology. So I've actually learned the manifold structure. This is what manifold learning is. And under these kind of conditions here, after you've got enough points, you've actually learned it with the correct topology.
together, they form a submanifold atlas, you said?
They form, they form an atlas of submanifold charts. Yep. Which is itself an atlas just on the set of points as a topological space. Now, the cool thing is each of these linear regressions you can compute using just plain old linear regressions, however you want to do that. So the whole thing is now pulled out. We've got this very nice structure that you can then do all the kinds of computations you'd like to do. Now you can do calculus on this set of points. You can do sensitivity analyses. Do perturbations. You want to do some kind of question about what do you do with regression often? You want to know how the various correlations are fit together. You understand that locally, but now you can make assertions about the fact that this point here is so far away from here, I can't fit them together from a correlation standpoint. Because there's no reason to make them correlate because they just aren't. Whereby a global regression is the wrong thing to do, local regression is the right thing to do.
And so you have a massive jump in explanatory power, right, in
That's
your
right.
regressions.
That's right. You have a massive jump in your explanatory power because each of these regressions are much, much better quality. Yes, exactly.
Okay,
How
so,
do you define the parameters of that, of the circle? So
This circle,
yeah, well, how do you?
set of all points, distance, whatever, less than k, say.
because they live in Rn, so you.
They live in Rn,
Distance.
so I've got a distance.
Right,
Yep.
how do you sample your, so you construct like these balls around your
Take
points?
a random sample of points out of your original data set.
Right, like
Those are
we
your
discussed the
sectors.
other day, you can just make a chart of them and then sample. Or
Make a table of them.
Yeah,
Just
break them.
randomly sample the rows out of that table.
Right, so, yeah, you enumerate them, create a bijection between them and some set. And then-
Yep. Just yank out a bunch of them, you're good to go. That's right, yeah.
It often happens in surveys that certain populations don't show up in the surveys. Because you
Sure.
try to count everybody, but
Yep.
your ability to count
Yep.
people is
So
correlated
those
with their
can show,
demographics.
if, those would, in some cases, not always, but in some cases, topological defects, as in the homology,
So,
is non-trivial, for instance here. No, not always. You have to look at your data to understand exactly why. But yes, this has been proposed by various authors as a means for identifying populations that you've missed in your sampling. Absolutely. If this is dynamical data, this picks up things that are kind of periodic, but normal periodic analysis, like Fourier analysis, requires actual periodicity, or almost periodicity, which is to say that usually the period is about this. This allows you to study things that the period changes dramatically. That's not a periodic function. If I cycle around this thing slowly and I start speeding up and keep speeding up, there is no period to speak of at all. Yet you can still detect that kind of periodicity. And there are much more intricate things as well that can be pulled out of this kind of data. I think that's a good place to stop. So, next up, last lecture of the course as it happens is on Wednesday. I'm going to give a little bit of a view to the future. Talk a little bit about sheaves and how they fit in topological space.